Hello, pre-calculus students. Today we are going to talk about section 3.5. So please make sure you have your notes, something to write with, and you will want a graphing calculator. Oh my gosh, every time I want to try to share my dot cam, it happens every time. It makes me crazy, guys. I swear I know sort of what I'm doing, but every time I want to share my dot cam, the first time I do it, it just doesn't agree with me. And now it's not there at all. All right, hang on a second. All right, so while I'm dealing with this, you are getting out your stuff, right? Goodness. I don't know why it does this to me. All right, there it is. I see it. There we go. Oh my goodness. Okay. So we're going to talk about continuity and we're going to talk about end behavior. At the beginning of the chapter, we talked a tiny bit about the baby definition for continuity, and that is that the function cannot be traced without lifting your pencil. So here we have three examples of discontinuous functions. Okay, so here it has this branch and it has this branch. So I would have to lift my pencil to trace. Here it has this little section, and then I'd have to jump to get to this little section. Here I have this, and then I have to skip over that point, and then I keep going. So in all of these three cases, they're considered discontinuous. And we are going to be talking about discontinuous at a particular value, and we're going to refer to that value we're checking for discontinuity at as the value x equals c. So this right here is an example of having a discontinuity at x equals 0, right? At 0, that's where I'm having to lift my pencil to get to the other section. Here's the function I have. Notice that in this discontinuity, I have a vertical asymptote. So we have our three different types of discontinuities we're going to talk about. We're going to talk about infinite discontinuities, jump discontinuities, and point discontinuities. In an infinite discontinuity, it always shows up in the graph as a vertical asymptote. Okay, and so the place where we have that vertical asymptote is going to always happen at the value that makes the denominator 0. So at the value where the denominator is 0, so at x equals c, it's going to give 0 in the denominator. Okay, so in a jump discontinuity, what is happening is as I approach this, here's where I have my discontinuity at 0 again. As I approach that value 0, I jump from one y value to another y value. So it's not that something is undefined, it's that there are two different y values happening at the same x value, kind of. Okay, these are both open circles, so technically those aren't included. Now, the function that we have here is this piecewise function. So this little part of the graph here follows the first rule, so x squared plus 1 when x is less than 0. So that's this little parabola here. And then we follow the rule y equals x when for x values bigger than 0. And so at 0, if I were to plug 0 into each of these rules, and now I know this says less than 0 or greater than 0, but it could be like 0.01, right? Or negative 0.01. It could be really close to being 0 on the positive or negative side. So we're just going to put 0 in and use an open circle to show it doesn't include it. But if I put 0 here, I get 1. If I put 0 here, I get 0. And so the two pieces don't match up. So this is a jump discontinuity. So these are often piecewise, not always, but often piecewise. If you think back also to our parent functions, we also had a step function. Those would also be considered jump discontinuities. Okay, so I'm going to put step functions here too, or step functions. Okay, but not every piecewise function is a jump discontinuity, and we'll see examples of that. Sometimes the two pieces might line up. So don't just think because you have a rule like this that it's automatically jump. It could actually be continuous. Okay, so what's happening is at x equals c, you're approaching two different y values. So as you come at that value from the left and the right, you're approaching two different y values. So at x equals c, you're approaching two different y values. All right, and then the last type of discontinuity is a point discontinuity. So it's almost like we have a continuous graph, but this one single point is an open circle. And if we look to our equation, which I know it's kind of small here, so I've rewritten it here. If we look to our equation, notice what happens. If I were to factor this numerator, I would get x plus 1 times x minus 1 all over x plus 1. And then see what happens is those factors cancel, and this is equivalent to f of x equals x minus 1, with the one criteria that x cannot equal -1, because in my original function, that's a discontinuity, right? That's not possible. Discontinuities, oftentimes when you have, well, always when you have a rational function, it always happens when you have a 0 in the denominator. And what gives me a 0 in the denominator is -1. But this equation here is a line. It's the line y equals x minus 1. So here's my line with a slope of 1 and a y-intercept of -1. But because it's discontinuous at -1, I have a hole in the graph. So it's also called a point discontinuity. So point discontinuities show up in the graph as a hole. And so that value at x equals c gives 0 in the denominator. And that is what happened over here also. So now we kind of have to talk a little bit about, well, how, so if it, in both cases, the c value where we have a discontinuity gave me 0 in the denominator, well, how am I going to know it's a vertical asymptote versus just being a hole in the graph? And we can look to our equations for a hint about that. Here, this x squared, there's nothing it can cancel with, right? So if I put 0 here, I get 0 in the denominator. That's not allowed. But this factor here, this on the bottom, doesn't cancel with anything from the top, whereas this did. And that's going to be the difference. So in an infinite discontinuity, it's that the factor does not cancel from the denominator. And later on in the chapter, we're going to refer to infinite discontinuities also as essential discontinuities. And I'm going to just mention that now, because when you think about that word essential, it's like it's necessary. You have to keep it, right? So here, that x squared, it's essential. I can't get rid of it. It doesn't cancel with anything. In something that's a point discontinuity, the factor does cancel from the denominator, cancels with something in the numerator. These are also going to be called removable discontinuities. And that word removable helps me remember what's going on here, because if I remove, right, I'm removing the value of the discontinuity, I'm canceling it out. That's what is giving me that hole in the graph, or the point. All right, so down here are some more formal descriptions of what's going on with each of these discontinuities. So another way we can describe the idea of having a vertical asymptote is that the absolute value of the function, right, so like the y values, become greater and greater as the graph approaches a given x value. Okay, that yields a vertical asymptote. So if I think about it, as these y values get bigger and bigger and bigger, they just keep going up, 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 right? So that means they're approaching this vertical asymptote. Okay, jump discontinuity, the graph stops at a given x value and then begins at a different y value. Point discontinuity, an x value for which a function is undefined, but the pieces of the graph match up, typically when a factor cancels from an equation. So we want a way to be able to look at a function and test whether or not it's continuous. And we're going to call this our continuity test. So to prove something is continuous, there are 3 things that have to happen. First of all, the function has to be defined at c, or in other words, f of c has to exist. So for example, in these two, at 0, that it wasn't even possible, you couldn't even plug it in. Actually, in this one, you can't either. If this one had like an equal to underneath it, then you could plug it in and you would say it's defined. This one would meet the first criteria if we had an equal to under it. Okay, so in all of these, we could start by saying, okay, I know it's not continuous because f of 0 isn't even possible. All right, the next criteria is that if it were possible, you have to approach the same y value on the left and the right-hand side of C. My of C kind of bumped down a little bit. It should be right next to it. So that means as I'm approaching my value or I'm checking for continuity, I have to approach the same y value as I approach from the left and from the right. Okay, that doesn't happen in this one. As I approach from the left, I'm getting closer to 1. As I approach from the right, my y value is getting closer to 0. When that happens, I know it's a jump discontinuity. In this one, this does meet the second criteria because as I approach this value from the left, I get closer to -2, I think it is. And as I approach from the right, I get closer to -2. So that is the same. And you know what? I just realized, I think I said something about them all being discontinuous at 0, realizing this is actually discontinuous at -1. Just so if you were like, hang on, what is she talking about? All right, and then the last one is that the y value that the function approaches from each side has to equal f of c. So whatever value you got here, as you approach from the left and the right, it has to be the same as that number that you got from step 1. Okay, so then our next step is going to be to practice with this continuity test. So we want to determine whether or not these 3 functions are continuous. And it is asking if it's continuous at that given x value. So here's the function. I want to know if it's continuous at x equals 1. Here I want to know if this one is continuous at x equals -2. Here I forgot to ask you if it's continuous at x equals -2. So we're going to add that in here. Okay, so as we go through the continuity test, the first thing we're asking ourselves is, does, in this case, f of 1 exist? Okay, here I'm asking myself, does f of -2 exist? Here, does f of -2 exist? Okay. Once you have failed one of those criteria, you're done. Like, you don't have to disprove the other ones. Failing one of them is enough to say it's not continuous. Okay, so just start out with that first one, see if you can decide, okay, do we need to proceed to the next part? Okay, so for this one, if I plug 1 in, so f of 1 would be 3 times 1 squared plus 1 minus 7. So that's 3 plus 1 is 4. Minus 7, so that's -3. Okay, so that one meets that criteria. For this one, if I do f of -2, so if I do -2 squared minus 4 over -2 plus 2, I get a 0 in the denominator, right? That's not possible. So this is discontinuous or not continuous. Now, we need to talk about what type of discontinuity it is. So remember, if it's discontinuity, it could be point, it could be jump, or it could be infinite. And we said jump is usually piecewise, and then if it's rational, it's usually infinite or point. And how we decided was, okay, we know that this makes the bottom 0, so it's either infinite or point. And the way we can tell them apart is whether or not a factor cancels from the top and the bottom. So I'm going to factor my top here. Oh, I see this cancels at x equals -2, right? This would cancel for the x plus 2. So that makes us a point discontinuity. Okay, now this one, does f of -2 exist? So when I look at this rule, this says plug into x squared if your x value is bigger than or equal to -2. Plug into this rule if x is less than -2. So you might be looking at this and saying, oh, wait, I'm gonna put this in there. It doesn't exist. But this rule says I should be plugging the -2 in up here. So -2 squared is 4. Okay, that does exist. Okay, so now let's go back here and step 2 is that as I approach this value of 1 from the left and from the right, it has to approach the same value. And step 3 is if this value here is the same as step 1, so the value from step 1 equals the value from step 2, if those are the same, then it's continuous. So that's what I need to check. Now, a lot of times it's going to be helpful to look at the graph. Okay, so I'm going to just pull this up in Desmos. Okay, so what do we have here? 3x, whoops, helps to be in the window there, 3x squared plus x minus 7. Okay, now I am interested in this when x equals 1. So here's x equals 1 is right here. Here's x equals 1. Actually, I think what I'm going to do here is I'm going to write x equals 1. I'm just going to graph that. I'm going to graph that. And there, I'm going to do that. Okay, so I just graphed it. I made it dashed because that's not technically part of our graph, but I just want you to really focus in on here's where x is 1 and what's happening on either side of this parabola. So now when I talk about from the left and from the right, here's the left side of x equals 1 over here. And if I start up here and I trace along the graph, my question is, what is happening to the y values? What are the y values doing? So here they're going down, right? They come back up. What y value are we getting closer and closer and closer and closer to? Right here, we're getting closer and closer to -3. Okay, so that's what I'm approaching from the left, and I'm going to jot that down on my paper. And now how about from the right? If I start over here on the right side of x equals 1. So if I start over here and I start heading towards the x equals 1 along my graph, what y value am I getting closer and closer and closer and closer to? I'm getting closer and closer and closer to -3 again. So remember my criteria for step 2 was that I had to be approaching the same value from the left and the right, and I am. I'm approaching -3 in both cases. Now, step 3 of my continuity test is that the value from step 1 has to equal the value from step 2. And those values are equal, so it's met all 3 criteria. It existed, the left and right. We're going to call those limits from the left and the right as we move forward this semester. And then those values are equal, so this is a continuous function. And you might have been thinking all along, it's a parabola. I knew it was continuous. Okay, but here's how we could verify that it's continuous. Okay, so now if we look at this next one, we already did step 1 where we said, okay, yes, it exists. So now the next thing to do is look at this from the left and from the right, what's going on. Okay, I'm going to go back to Desmos and I'll show you how you can enter this in and put in those restrictions about like when x is bigger than or equal to 2 and when x is less than negative 2 it is. Okay, so I'm going to first just enter y equals x squared. And then in the braces, so the squiggly bracket, whoops, not as the power, you got to bump down. Okay, in the braces, I'm going to type x and then greater than or equal to, which you could use this keypad down here to get the greater than or equal to. So that's one way to do that. I'll show you another way in a second. And then -2, okay, and then you can close your brace, or if you just go down, it closes the brace. Do you see how now it's only graphing this rule when x is to the right of the -2. All right, another way that you could have gotten this greater than or equal to is you could have literally typed the greater than symbol and then hit equal, and then we'll put the equal to underneath it. So if you don't want, if you're on your phone sometimes, or no, I guess on the phone you'd want the keyboard. But anyway, there you go. If you're on a keyboard, that works. Okay, so then for my second part, so y equals 1 over and then x squared minus 4. Okay, so this looks crazy right now. I'm going to put in the restriction of x is less than -2, and that will clean up some of that mess. Okay, so as we approach from the left and the right, what is going on? So from the left, what does it seem like is going on? So here's the left, here is, and I'm gonna just go ahead and put in, what was it, x equals -2. I'm just going to do that so that you guys can see exactly where I'm talking about. Okay, so here, this dashed line here is the x is -2, just so you can see, okay, this is what we're talking about approaching. So here's to the left of x equals -2, and this right here is up, 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 and it's going up forever and ever and ever. This was that, it was a branch, right? It kept going. So the limit of that is just infinity. It's undefined, right? It's so the limit from the right is it got a vertical asymptote, right? Now from the left, what is happening? It's getting closer and closer to what y value is getting closer and closer to 4. Well, those aren't the same, right? Those aren't the same things that they're approaching. And so then that's a way that we can verify that this is not continuous, right? From the left is one value, from the right is another value, right? It's got a vertical asymptote. Okay, so these are not equal, so this is discontinuous. And when they're not equal from the left and the right, that's a jump discontinuity. Now, another way you could check this without graphing is you could put the -2 into both rules. Now, I know we talked about technically it should be going into this rule, but if you plug it into this rule, because it could be anything right up until the -2, just not including it, it would just mean there's an open circle. Here, if you put -2 in, you get 4, right? -2 squared is 4. Oh, I think I wrote these down backwards. I did. And then when you go to put it in on the other side, it's undefined, right? And so that's another way you could confirm it. Okay, you could also, on your graphing calculator, if you're using an Inspire, you can also do the trick with the restricting the domain. So the first thing that you can do is if you go to the grouping symbol menu, which is next to the number 9, so right here next to the number 9, and you look, it's in the top row, and it has it has a brace, and then it has a little box, then a comma, then and on the bottom it has a box and a comma, and you pick that. Then in the top box, we could type in the x squared, and then if we tab over, then we can enter in that restriction of what was it, x is bigger than or equal to -2. So we type in the x, and then under the control key where it has the equal sign, you see how there's all those symbols? So you hit control equals, and then there's where the greater than or equal to is, and then -2, and then tab. And then here I could type in my 1 over x squared minus 4, and then tab over, and then do x, and then control equals to get to that menu again. And now it's less than, correct? Less than -2. And then you get the same thing. It gets you the same thing. Just be careful though with this and also with decimals, because technically when it's a less than, you should be having like an open circle, or you have the asymptote or whatever. It's not going to show like if there should be an open circle, sort of like when we had the graph on the other page, how it had the 2 open circles, or how this one here, has an open circle and that one doesn't. It won't show that on decimals or on your graphing calculator because it connects pixels. All right, so this next one, a function may have a discontinuity at 1 or more x values, but be continuous on an interval of other x values. So this is discontinuous right here at 2. We see there's a jump discontinuity. But if I just said, hey, is it continuous at -2? Right here, we have no holes, we have no breaks, we have no asymptotes. It could be continuous on a separate interval, right? I could say it's continuous from -infinity to 2 or something like that. Okay, so that's what this, a function is continuous on an interval if and only if it is continuous at each number on that interval. So I could say it's continuous from like -infinity to 2, and then it's continuous from, anything bigger than 2 to infinity. All right, so if we look at example 2, it says a shipping company offers insurance for its express delivery service for a package valued at no more than $500. Insurance is included in the $12 fee. Then for 501 to 5,000, it costs an additional 95 cents per $100 of value. This graph summarizes the cost. So this is kind of how packaging works in general. Like when you buy a stamp, that stamp is for anything from 0 to 1 ounce. Anything over 1 ounce, then you're going to have to put, an additional however many cents from 1 ounces to 2 ounces. So you get these step functions. So it says use a continuity test to show that the step function is discontinuous. Okay, so let's say we wanted to check if it was discontinuous. I'm going to give you a value, let's say at 500. So I want you to take a minute and think through those 3 steps. So try the continuity test out on this. Okay, so first of all, at 500, does f of 500 exist? So if I said, what is f of 500? You would go to 500, and here's the closed circle versus the open circle. You'd say, yeah, that exists, it's 12. All right, now, as I approach, so my second step is I approach 500 from the left, And from the right, what am I getting closer to? Okay, so here's my 500. As I approach that 500 from the left, headed towards the 500, the Y value I'm getting closer to is $12. As I approach this 500 from the right, heading towards the 500, right? So I start up here and then I jump and 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 I jump here. As I get closer and closer to the 500, my Y value actually gets closer to this right here. Looks like 13, but it was 95 cents, right? So it's $12.95. Right, so you might be saying, well, hang on though, at 500, that's an open circle. It's not a question of what does it equal at 500, it's what is it getting closer to from the right. It's getting closer to $12.95. Since these are not equal, this means we have a jump discontinuity. Okay. All right, and why a continuous function would not be appropriate to model this, you would have to have something like maybe increasing like this, right? And when you talk about package costs, it's usually, or weights or whatever, you're usually doing them on intervals, not like 12.1 ounces, 12.2 ounces, 12.3 ounces. It's usually on an interval, so that's why that doesn't make sense. Okay, one last thing that we need to talk about in this section at the top of the next page here I have is intervals where a function's increasing and decreasing. One second. Sorry, not increasing and decreasing. I knew something was wrong. I had to check my notes. First, we're going to do end behavior and then increasing, decreasing. You know what? I am going to make a separate video for that because it's getting too long. Okay, so next video is going to be end behavior and increasing, decreasing. Sorry for getting you all excited for it, and I'm going to put it in a separate video.